Today we are going to discuss about the introduction to DC converters. So let us start the session today. These converters are the static devices. They going to convert the fixed DC input voltage to a variable DC output voltage. In the input side we are having the input fixed supply, DC supply, and the output you will find a variable DC supply. These DC to DC converter consist of different components like semiconductor switches, especially MOSFETs, IGBTs and BJTs, and the filter components. We are using the inductive filter, capacitive filters and diodes. Features. So let us talk about the features first. We got the regulated DC output supply. They are having the switch mode operations. Because of that, these switch mode operation, their switching frequency, efficiency is very high. We can find it a step up DC to DC converter. They can have a step down topology. They can have both, and they can have the inverse also. The PWM control is possible here. Especially we are using the MOSFET and IGBTs in order to design these converters. They can operate at high switching frequency greater than 220 kilohertz. Closed loop, precise and smooth control is possible. So these are the features. Let us talk about the applications very widely used in power supplies, such as personal computers, and the office equipments, spacecraft power systems, laptops. We are having these DC to DC converters. Telecommunication equipments is also having the same. Mainly used in power supplies in different applications. It is also used in DC motor drives and traction motor control in our electric traction systems. It is also used in battery operated vehicles such as EVs, trolley cars, and it can also be applied where the electric backing is required. Some merits and demerits of these DC to DC converters. These DC to DC converters having the higher efficiencies, like between the 70% to 98% in all practical cases. It can operate high switching frequency. So typical frequency range for these converters is 1 kilohertz to 1 megahertz. These converters having the high power density. These converters having low cost, easy to control. They can possess a fast dynamic response. In spite of these advantages, we can have some disadvantage also here, like complicated structure, and because it can operate high switching frequency, so high electromagnetic interference is generated here. In short, it is called high EMI. Converters, broadly we can classify these converter into two categories: non-isolated type and isolated type. In this session we are discussing about the non-isolated type DC to DC converters only. Non-isolated type DC to DC converters very small in size, lighter in weight, and having the lower cost as compared to the isolated ones. On the other side, the isolated type converters, these converters having the better noise filter ability and efficiently convert the voltage with high ratio. So let us discuss more about the non-isolated type converters. There are various types of topologies for these non-isolated type DC to DC converters. Under this category we are having the 5 to 6 topologies. Some are summarized here, such as buck converter, boost converter, buck boost converter, Cuck converter, zeta converter and Sepik converter. This Sepik converter is your single inlet primary inductor converter. So in this session we are only considering the buck and boost converter. Buck converter is very basic DC to DC converter, step down converter, and boost is your step up converter. So let us start with the very basic converter known as buck converter. It is a non-isolated type step down DC to DC converter. You can see here, this is our switch. This is our switch. We are using one switch here. This is a power electronic switch, which is also called solid state switch or semiconductor switch. The input side is having this is our input side. This is our input side. And we are going to supply this converter a DC voltage. And one diode is used here, one inductor is used here, one capacitor is used here, and this is our load. These are the components by which we can have the design a buck converter. We can connect a MOSFET here. We have connected a MOSFET here. This is our MOSFET. So MOSFET is connected as a switch here. Depending upon the on and off, we will get the output voltage. About the operation of this buck converter, when the switch is on, in the first figure you can see here, this is our first figure, first diagram. You can see here during on state, this is our on state when switch is behaving like a closed switch. So input power, input DC power is supplied to the load through this filter. This is our filter circuit, LNC as a filter circuit, and the power which is supplied from the input is going to the output. Okay, during on state, load is getting the power from the source, and during off state, this load is carrying the current through this diode, inductor and then load. So that means during the on state of switch, the power which is stored during on state is now free-wheeled using this diode and filter circuit. So on other hand, you can see, so during on state, this is on state T on period. During on state, current is building up gradually, and then during off state, current is gradually decreasing, and this process is keep on repeating, and this we will get a current at the load side. In order to get more into it, these are some waveforms. This is the on time, this is the off time, this is our input voltage, this is our input voltage, this is our output voltage. In the blue line, this is our output voltage, average output voltage, and yellow area, this is this area, and dark yellow area is your inductor voltage. So during on state, the inductor voltage is this, and during off state, inductor voltage is negative and shown here as dark yellow region. So during off state, inductor voltage is minus V0, or during on state, the voltage across the inductor is Vi minus V0. So as like previous case, our current is increasing during the T on period, and current is decreasing during the T off period. This is our on period, this much is our on period, and this is our off period till here. Off period, this is on period. So when the switch is closed, the voltage across the inductor, as I told you, Vi minus V naught, and when the switch is open or off, the voltage across the inductor is minus V naught. Here Vi is the input voltage and V naught is your output voltage. If you are trying to write the voltage second, or it is also called volt second balance equation for this inductor, so this is V in or input voltage minus V naught upon L into T on minus V naught upon L into T off equal to 0. This is our volt second balance equation for the inductor. After rearranging, we will get V naught is equal to T on upon T on plus T off into V in. V in means input voltage. If you are going to more simplify it, T on upon T, this is total time, into V. This factor T upon T can be written as capital D, which is nothing but the duty cycle. This is our duty cycle. This is our duty cycle. That means for the buck operation or buck converter, output voltage is equal to the duty cycle times input voltage. This is our relation for buck converter. Trying to draw the DC output voltage versus the duty cycle graph, you will find in this scale, y-axis we are taking output voltage and the x-axis we are taking the duty cycle. So as we increase the duty cycle, you can also see the output voltage is also going to be increased gradually. So limit of the duty cycle means this is the duty cycle. It starts from 0 till 1 only. So duty cycle limit will be between 0 to 1 only. So as we increase the duty cycle, your output voltage is also going to increase. For the buck operation, you can say output voltage is always less than the input voltage. So you can control the output voltage within this limit only till Vi. Suppose at the input you are having the 15 volt. At the input side you have applied the 15 volt. So you are getting the output voltage between the 0 to 15 volts only. This is 0. If it is a 15, so this output voltage control limits between the output voltage is regulated between 0 to 15 only. Your output voltage never going to be exceed the input voltage. For this example, if we are taking the 15 volt input, so it cannot be exceed the 15 volt. In this figure, I am showing here how this average voltage is going to be increased. So as we keep on increasing the duty cycle, if it is 25%, there will be the average voltage here only, here in this limit only. If we are increase the duty cycle 50%, then our average output voltage is also going to be increased. As we keep on increasing the duty cycle, you can see average output voltage is also going to be increased. So if it is 100%, if it is 100% duty cycle, so V out is equal to V So input voltage and output voltage is equal to the input voltage. This is the relation between the duty cycle and output voltage. Functioning and working of buck converter. When the switch is on, input is supplying the power to the output. When the switch is off, the saved energy during the on time in the load circuit will now going to be freewheeled using the diode and filter circuit. In the buck operation, output voltage is always less than the input voltage. So this is the functioning, all about the functioning. How we can control the DC to DC converters? The DC to DC converter can be controlled using the duty cycle. Duty cycle D is defined as the ratio of on time to the total time T. By varying the duty cycle, can control the output of DC to DC converter. There are basically two types of control methods or strategy to control the output of DC to DC converter. First method is time ratio control, TRC. Second is your current limit control method, CLC. In this session, we are talking about the time ratio control only. We are not going to discuss about the current limit control. Basically, in the current limit control, we have defined the band here actually. In the current limit control, we are defining the upper limit and lower limit of the current, load current, and our load current is just moving between these two. This is our upper limit, this is our lower limit. If our load current is moving beyond this upper limit, then switch is going to be off, and when the switch is off, then current going to be decreased gradually. When it reaches to the lower level, then again switch is on, and again it forcing the current to increase like this only. So this will keep on increasing. So in this session, we are not going to talk more about this CLC, current limit control method. So let us discuss about the time ratio control method. In the time ratio TRC method, the value of T on upon T, it is nothing but the duty cycle or the duty ratio. It is varied in order to change the average output voltage of the converter. Here we are having the two methods. Under this TRC, two ways we can apply this method. First one is your constant frequency, second is your variable frequency. In the constant frequency, we are just keeping time period T or frequency constant, and we are going to vary the T on. This is also called a pulse width modulation. This is also known as pulse width modulation. Constant frequency method is also known as pulse width modulation. Here in this method, we are just varying the pulses. These are the pulses. These are the pulses. If I varying the width of the pulse, that means we are increasing the T on time. We are increasing the T on time. Keeping, this is our pulse. This is T on time. These are the next pulse. So this is your T. So our T is fixed. This is fixed quantity. This T is fixed. And I am varying the pulse width. That means I am varying the T on. By varying the T on, our width of the pulse is going to be varied. That's why this constant frequency method is also called the pulse width modulation. In other method, under this TRC, we are having the variable frequency method. Variable frequency method means I am not keeping this T or F constant. It is going to be varied, but we are fixing here. we are fixing here in this method T on or T off. Either I am fixing T on or I am going to fix T off. Any one of these two quantities, T on or T off, is fixed, but I am varying the T or F. This, because either here frequency is variable, so that's why it is called this method is also called a frequency modulation, in short FM. So under TRC we are having the two methods: constant frequency, also known as pulse width modulation, and the variable frequency method, also called a frequency modulation. Under constant frequency, we are keeping T constant or frequency constant. I am varying the T on time. If the T on timing is variable, that means I am varying the width of the pulses. In the variable frequency method, the frequency is variable and keeping T on or T off fixed. This is the method which I also called a frequency modulation. Discuss more about the how we can control the output voltage. This is the buck converter. Input side we have applied the Vi. This is our switch. This Q1 is your MOSFET acting as a switch. MOSFET. We have applied a DC voltage here Vi, and this is our output voltage V0. If you want to regulate the output voltage or control the output voltage, we can sense the output voltage. In this feedback, in this line is shown here. I am just measuring the voltage here by using potential divider or sensor circuits. This HS is the gain of this feedback circuit. In this point we have a measured output voltage. This is our measured output voltage. Measured output voltage. We have measured the output voltage and it is compared with the reference input. This is our reference. Suppose our reference is 20 volts. I want to maintain here 20 volts. I am measuring the voltage whether it is a 20 volt or not. I am getting 18 volt. I am getting 18 volt here, but I will try to maintain 20 volt. I am taking 20 volt as a reference. In particular application, I want the 20 volt to be maintained in the output side, but after measuring I am getting 18 volt. So I am putting this feedback as a controlled feedback loop. Okay. So I am measuring the output voltage by using sensor or potential divider circuits. So this measured voltage here at this point is now compared with the reference one, and the error signal is generated. Here error is generated. How much? 2 volts error is generated. So depending upon this error signal, it is fed to a controller. This is controller. This is controller circuit. In most of the drive circuit is a PI controller. It can also called a compensator. So depending upon this error signal, this controller give the output voltage or give the reference output voltage. What should be the reference output voltage? It will give. And this reference, what we will get the controller is now going to supply to the pulse width modulator. In the pulse width modulation block, we are having a carrier waves like this. Carrier waves are there, high frequency carrier waves are there, and we are supplying a reference signal. This is our reference signal VC, what we have getting here at the output of the controller, and this VC is now compared with these high frequency carrier waves. So these two are generating the pulses as per the logic. When the VC is greater than the carrier wave, then output is 1, otherwise 0. So like this only we are getting the pulses. Like this we are getting the pulses. Like this. So pulses are generated accordingly, according to the ref. So if the references got changed, the pulse width also going to be changed like this only. So that's why it is called a pulse width modulator. So pulses are generated like this only, and then it is going to be buffer circuit or driver circuit which drives this MOSFET, or control this MOSFET. So according to the pulse generated here, it will control the duty cycle of this MOSFET, and accordingly we will get the output voltage equal to the reference voltage 20. So this is the way how we can control the buck converter. Again, I'm just summarizing this whole concept. Here at the output side we are measuring the output voltage. Now measured output voltage is compared with the reference one, and the error signal is generated after feeding to the controller. Depending upon the error signal, this controller will give the reference signal, and then reference signal is going to the pulse width modulator as an input, where it is compared with the high frequency carrier waves, and after comparing, the pulses is going to be generated, which is going to drive the MOSFET. This is the whole control of buck converter. So like this only we can control the boost converter also. Control is same. The functioning is somewhat different, but control is same. Converter. What is boost converter? It is also a non-isolated type step up DC to DC converter, similar to the buck converter, but here the output voltage is somewhat higher than the input. In the left side, this is a basic boost converter, and in the second figure in this side we are using the MOSFET. This is our MOSFET. So boost converter using a MOSFET, and other circuit a simple switch is shown here. Trying to explain the functioning. When the switch is on, the inductor is this inductor. When the switch is on, this is our inductor. When the switch is on, inductor stores the energy. Because now the path is only to the inductor, then switch, then again going back to the source. When the switch is on, this is the path only one loop: source, inductor, switch, and back to the source. In this on period, inductor stores the energy, and during off period, when the switch is off, this diode will going to be forward bias, because inductor voltage, this side positive and this side negative. It makes the diode forward bias and it will start conducting and try to supply the load. And because load is supplied by the input voltage plus stored energy or during the turn on time, so the load will having the Vs plus inductor voltage. So that means during off period of the switch, load will supplied by the source plus stored energy in the inductor. In a more detailed operation, here we have shown the diagrams how it is functioning. In the left hand figure, in the left hand side, in this side, this is on period. During the on period, this is the way how the current is flowing. In this time, inductor stores the energy, and during off time, inductor stored energy plus input energy supplied by the source, these two are imposed in the load side. This is negative and this is positive during off. So during on time, when current is trying to build up gradually, so inductor generated voltage is try to oppose the current build up. That's why this is positive and this is negative. It will try to oppose the current build up because current is increasing here. During off time, current is try to decrease because already build up is happened. Now it is during off period, it is going to be decreased, and because current is decreasing, again this polarity is reversed, this side positive and this side negative. Because this side positive, this makes this diode forward bias, and your load will supplied by both of the energy, input side energy plus stored energy in the inductor. In other words, your load is supplied by V in plus inductor voltage. It is more specifically V in plus L di by dt. This is the voltage across the inductor. So in all cases, V out is all greater than the V input. In all cases, the output voltage is always greater than the input voltage. That's why it is called a boost converter. Output voltage is always greater than the input voltage. Let us understand this by example. If you have applied a 15 volt, you will definitely get the output voltage between 15 to 30 volt at least. That means your spanning range at the output will starts from 15 and onwards. Boost converter input output relation is given like V out is equal to 1 upon 1 minus d V in. Here d is your duty cycle. Okay, d is your duty cycle. The output voltage can be calculated like 1 upon 1 minus d into V in. This is your input output relationship. So this is all about the buck and boost converters. So thank you.